Now let us study the next set of integrals. Now these are also of a very similar nature as compared to the previous, except that now there is a square root sign. So in this, let us study the first one, which is integral of 1 upon root of a square minus x square. So once again here a stands for some real constant and x is the variable of integration. Now to solve this, we put x as a sine theta. Now once again this will be clear why we are doing that, because if we look at the denominator term on substitution, that will give us a square cos square theta. Alright, so dx is a cos theta d theta. So therefore on substitution we get integral as 1 upon root of a square minus x square will be nothing but a square sine square theta multiplied by dx is a cos theta d theta, right? That is equal to integral of 1 upon. Now inside the square root, taking a square common, we have 1 minus sine square theta, which is cos square theta. So therefore square root of a square cos square theta is a cos theta multiplied with, we already have a cos theta in the numerator. So therefore everything gets cancelled and we are left with just d theta. So that is nothing but theta plus c, and we now have to resubstitute theta in terms of x. So for that we see that we had put x as a sine theta, so therefore that gives us sine theta to be equal to x upon a, correct? So therefore we have theta as equal to sine inverse of x by a, correct? So this is the value of theta that we substitute in the final answer. So therefore that is equal to sine inverse of x by a. So if we compare this with one of the previous results that we had seen, there it was tan inverse of x by a, but there was a term of 1 upon a also as a multiplier. So here there is no 1 upon a outside. Alright, so it is simply sine inverse of x by a, which is the answer. Now let's move ahead and see the remaining two combinations. That is, here also we have the denominator and square root, but the terms are x square minus a square or x square plus a square. Once again we do this by substitution method only. Suppose we want to solve the first out of the two. Now as you would have guessed, that is, since we have x square minus a square, we have a minus term, so therefore we must put x as a sec theta, because sec square minus 1 is tan square. So dx gives us on differentiation a sec theta tan theta d theta, right? So therefore the integral becomes 1 upon root of x square is a square sec square theta minus a square into dx is a sec theta tan theta d theta, right? So that gives us 1 upon. Now inside the root, taking a square common, we have sec square theta minus 1, which is tan square theta. So that is root of a square tan square theta. So taking root, we have just a tan theta in the denominator multiplied with a sec theta tan theta d theta, right? So here a tan theta gets cancelled and we are left with simply sec theta. and we know that the integral of sec theta, which is a standard result, that is log of sec theta plus tan theta. Isn't it? So that's the answer, but we must write the answer in terms of x because theta is the substitution variable. So now to do that, let us understand that sec theta can be written as x by a. So that means we want to convert all the trigonometric terms into sec theta, which can be easily replaced with x by a. So if you observe, we have already got one term which is sec theta. The only remaining term is tan theta, and we know that tan theta can be easily written in terms of sec theta by the well-known identity. So let us do that and substitute sec theta plus, now here tan theta can be written as root of sec square theta minus 1, right, plus c. So therefore now let us substitute that. So integral becomes log of mod of, now in place of sec theta we can write x upon a plus root of, now sec square theta is nothing but x square upon a square, right, minus 1 plus c. So simplifying that further, we will get log of mod of, now if you observe in the square root sign, if we take a square as the common LCM, then we will get x square minus a square whole upon a square. So the denominator a square can be taken outside the root, and we can merge the two fractions as x plus square root of x square minus a square whole upon a plus c. Now simplifying that further, what we can do is, this is of the form log of x upon log of y, something like that. So since we have a division of the terms inside the log, we can break it as log of x plus x square minus a square inside the root, and then I can do minus of log a because that's the term in the denominator, plus c. Now if you see, log a is also some constant because a itself is a constant. So therefore the last two terms can be definitely merged into another constant, which is ultimately a constant only. So therefore our final answer is nothing but log of mod of x plus root of x square minus a square. Now we can definitely denote the previously obtained constant as say c1, so that now the new constant which we have got, that is minus log a plus c1, we can just write it as a single constant, which is c. So therefore this is the final answer of the given integral. The other integral, in which we have 1 upon root of x square plus a square, also has exactly similar procedure, except that we will substitute x as a tan theta because we have the plus sign here, and at the end the answer also is of almost similar type as we have obtained here. The only difference will be in the sign inside the square root sign. All the rest of the terms will be exactly same. So let us recap these last three results also once again. So here we have the first, second and third result. That is, first is integral of 1 upon root of a square minus x square is sine inverse of x by a. then integral of 1 upon root of x square minus a square is log of mod of x plus root of x square minus a square. And lastly, integral of 1 upon root of x square plus a square is log of mod of x plus root of x square plus a square. So a good way to remember the last two results is that whatever is the square root, the same appears in its integral also. And the other two terms are also exactly of the same type. So in this way we can remember these two results together.